This is the smallest yet most powerful water block in the world. Hello, my name is Daniel. I'm a thermal engineer, and today I will be talking about EMCOOL's Microfluidic block, which is a direct dye cooling solution capable of removing up to 500 watts of heat from a single silicon chip, while also maintaining incredibly low temperatures. Here we have a side-to-side comparison between a conventional CPU water block and the EMCOOL's microfluidic block. As we can see here, the main difference is the size of the prints between the original IHS and just the silicon chip. As we can see here, uh, the size of the copper cooling layer is roughly the size of the original IHS. In this case is for the Core i9 14900K, and how we are removing the heat in a much smaller area. This is our microfluidic cooling block, as we call it. Why microfluidic? Because we are providing hundreds of micro pin fins, smaller than any other technologies out there, and also microfluidic because we are significantly reducing the size and footprint of the cooling solution. And as we can see here, the active cooling layer, which is indicated by this O-ring, is comparable to the size of my fingernail, right? We can see here, well, I mean, the camera is not showing, but we have hundreds of micro pin fins here that provide enough surface area to get rid of hundreds of watts of heat. We have a patent on this technology in which our main claim is that we are removing the heat directly at the source footprint, as we can see here. This is the main difference compared to other technologies. Okay, so let's talk about the installation process. We start by removing the ILM, or integrated loading mechanism. We can see here the main issue with this mechanism is that it only provides pressure at these 2 points, and therefore the cooling is not uniform across the chip. This has been documented by many people, and our cooling solution doesn't have that issue because it provides uniform contact across the whole chip. An important note here is to always keep the CPU in place while removing the loading mechanism, because if something falls and damages the motherboard pins, at that point is basically toast. So it's a good idea to always keep it here and use the provided Torx wrench to remove each of the screws for the ILM. Once you remove those 4 screws, you'll notice that the backplate falls from the motherboard. It's very important to keep this because we're going to use it to install our microfluidic block. Next, we need to make sure that the silicon chip is entirely clean. As we can see here, it's almost like a mirror. You can see my finger's reflection on the silicon surface. There are different ways to achieve this, which are not covered in this video because of the sake of simplicity. If you want to learn more about this, let us know. We have many materials to cover this. Next, we need to create a thin and uniform layer of liquid metal across the whole chip. We can start with a droplet about this size and being very careful not to spill the liquid metal and just cover the chip surface. Please be aware that you don't need to apply this in excess, because otherwise, I mean, it's common that many unexperienced people doing this think this is the standard thermal paste and end up with dead chips because they applied way too much liquid metal. So you can see here what's the amount that is required and the method. So let's just speed this up. For the next step, we need to apply another thin and uniform layer of liquid metal on the block's surface. As we can see here, I am using the remnant liquid metal that I use for the silicon chip. So we can see here, most of the times that will be enough just to create a very thin layer of liquid metal in order to match both surfaces. So what I'm doing is, of course, applying liquid metal in a area that is similar to that of the chip where we know the block is going to sit. Very important, we do not need to apply another droplet of liquid metal here, because otherwise we can have the risk of that liquid metal flowing and damaging the pins or other uh, electronic components on the chip. So if the amount that is left on the Q-tip is not enough, you can always grab some more from the silicon surface and reapply in order to create a layer about this size, as we can see here using this method. Next, we need to grab the CPU firmly by the edges. That's my suggestion, so you don't let the chip fall and make a mess, possibly kill your motherboard. Just put it like this. Make sure that the arrow is matching the CPU and the motherboard. As you can see here, it's definitely in its place. Okay, so for the next step, we need to firmly grab the block and carefully place it on top of the silicon chip. As we can see here, it's better to do it from a top view, so you can center the holes of the block with the holes of the backplate and place it like this. The surface tension will attach the copper and silicon surfaces. You will feel it, and then you can center the block as you would center the IHS, keeping in mind that this copper layer is about the same size of the IHS. Once you center this, you can proceed to install the screws. These 4 screws are provided with the block, keeping in mind that since the block and the backplate are already aligned, you can just drop them like this, and they should fall directly into the backplate's thread. The suggested procedure to install the block is to tighten the 4 screws in a cross pattern using only the force of your fingertips. As we can see here, I am screwing only with my fingertips, and I reach a point until I cannot further tighten the screws only with my fingertips. That means that we reach some level of torque for the screws, and this is our reference, so we can complete the installation by doing a 270-degree turn on each of the screws. But first, we just need to keep checking that neither of these 4 screws can be further tightened, only using the force of our fingertips. I'm just rechecking here, as you can notice, just making sure that neither of these screws move further down, and that's good enough to complete the next step. Once the block is installed, we need to build the PC and also complete the liquid cooling loop. Here's a fast forward process of these steps, which are not detailed here in this video since we are focusing on the block and its performance. So enjoy this short clips. For the detailed benchmarking, we have a 3-part video which is already published in our channel, in which we compared 3 different scenarios. The first one is using the preset settings on the motherboard. Second one, we use the AI overclocking, in which the motherboard characterizes the cooler, and based on that characterization, it gives a score to the cooler and provides a set of parameters for AI overclocking. And in the third one, we do manual overclocking. We push the CPU to the limit by overclocking to 5.9 and 6 gigahertz on all cores, at which point the power consumption is really high. It's about 420 watts of power or heat, which are successfully removed by our Waterblock. You can check those in our channel. In this video, what we're going to do is we're going to summarize or present the most relevant results by comparing our microfluidic block versus a commercial water block under the same conditions. The way we are going to compare the results is that we're going to have 2 timers on each side of the screen, and we're going to compare on the right the EMCOOL system, and on the left the commercial liquid cooling system. Both are going to be benchmarking the same CPU, which is the Core i9-14900K. Both systems are going to be running the same rendering task, which in this case is using the Cinebench R23 software. And both systems are going to be running on a 316 millimeter radiator and a D5 pump. What we're going to be looking on the right of the timers for each case are going to be the temperatures for both the performance and the efficient cores. And on the left side of the timers, we're going to be looking at the frequencies for both of these systems. So now that we know what are we going to be looking at in this side-to-side comparison, let's go for it in 3, 2, 1, go. We could start by noticing that the EMCOOL system is far ahead in the rendering task, while also if we compare the temperatures on the right, we can see that these are at least 25 degrees C cooler than the conventional liquid cooling system. For both the performance and efficient cores, the EMCOOL system already finished 1833 seconds, which is roughly 2 seconds faster than the conventional liquid cooling system, while also maintaining significantly lower temperatures, as we said, 25 degrees C cooler, and also offering roughly 4,000 points higher Cinebench score compared to the conventional liquid cooling system. Okay, so there you have it. Those are the impressive results you can get if you use our microfluidic block with direct die cooling. This block is compatible with Intel 12, 13, and 14 generation CPUs. The block is available in our website and also on Amazon. We are developing new products for direct die cooling of AMD CPUs, and also the newest generations of upcoming processors. So please stay tuned. If you like this video, please consider subscribing and liking the video. Let us know if you have any questions, such as what were the overclocking parameters, or any questions you may have. We'll be happy to ask those. Thank you.